Hello guys, we are back with another question from analysis in NBHM 2019. The question is as follows. We are given an enumeration of rationals in the interval 0, 1. The enumeration is R1, R2, Rn, and we have here it is defined a sequence of functions if n x. If n x is defined to be 1 if it is one of R1, R2, Rn and 0 otherwise. Then we are asked to find which of the following statements are true. Option A, the function fn is Riemann integrable over the interval 0 1 for each n belongs to n. That is for whether f1 is Riemann integrable, f2 is Riemann integrable, f3 is Riemann integrable, and so on. Option B, the sequence fn is pointwise convergent and limit function is Riemann integrable over the interval 0 1. C, the sequence fn is pointwise convergent but the limit function is not Riemann integrable over the interval 0 1. Obviously we can see option B and C cannot be simultaneously true. So for option A, we all know that theorem that if we have a function f a b to r which is bounded over the interval and continuous on AB except finite number of points in that interval, then f is integrable on that interval. So here if we focus on fn, so if d of fn denote the set of discontinuities of the function fn, then obviously we can see that where is fn discontinuous? There basically the points r1, r2, rn. So I am not proving that. That is very basic. For f1 there will be only one point r1, for f2 there will be r1, r2, for f3 r1, r2, r3, so on. So this is finite set. The discontinuity set of fn is finite. So by this theorem f is the Riemann integrable on AB, and so this option is correct. So next move to option B and C, for which we need the celebrated Lebesgue criteria. It is one of the most important theorem in measure theory or an integration theory for integrability. Which basically gives a necessary and sufficient condition for Riemann integrability. The theorem is as follows. F is a function defined on some closed and bounded domain, then f is Riemann integrable if and only if f is bounded and the set of discontinuities of f has measure 0. Okay, so here for that, first of all we need to find the limit function of fn. So we first find the limit function. So for when x is equal to some rational point, for suppose it is rk, then for all m greater or equal to k, the value of fm ax is basically, what is the definition of fx? It is 1 when x equal to r1, r2 up to rm. Since k is less than m, there will be somewhere inside, so and 0 otherwise. So fmx equal to fmrk equal to 1 for m greater or equal to k. So the limit of that sequence fn rk, so limit m going to infinity fm rk will be, here k is fixed. Once it is chosen, k is fixed. For suppose we first start with 1, then r2, then 3, and so on. So this is equal to 1. So f of x equal to 1 when x belongs to rational. R1 and R2 are basically enumeration for rational. So at each rational point the limit function is 1. And when x is irrational, that is basically 0 1 minus r1 r2 rn and so on, then fnx is equal to 0 for all n, because each f1x, if you focus on f1x, that point is never equal to r1, so that is 0. If you focus on f2x, that point is never equal to neither of r1 or r2, so that is 0, and so on. If you focus on fnx, x cannot be equal to any one of r1 r2 up to rn, so by definition of fnx it is going to be 0. So the limit function, limit fnx, that is fx, equal to 0 when x is irrational. So our limit function is basically 1 when x belongs to q and 0 when x belongs to, when x is irrational. So q complement intersection 0 1, and this is q intersection 0 1, because our domain is 0 1. So this is our limit function. And now here we see that fn pointwise converges to f. So we need to see whether our limit function is Riemann integrable. So only thing we check that the discontinuity set of f, and all you can see that the discontinuity set, if this is discontinuous at every point in 0 1, you can prove it. It is very basic. You can use sequential criteria, and that's very easy to prove it by using sequential criteria. I am not going to prove it. So you can prove it that f is discontinuous at each point. So discontinuity set by this notation, I am using this, discontinuity set of f is basically 0 to 1. So the measure of the discontinuity set of f is basically measure of this, and which is basically 1, so not equal to 0. So by using Lebesgue criteria, here f is bounded, with clearly bounded, and the set of discontinuity set is not of measure 0, so we can say that the limit function f is not Riemann integrable. So here the sequence of function pointwise convergent, yes, obviously this is true, because pointwise converges to that limit function f, this function, this function, and but f is not Riemann integrable. The limit function is not Riemann integrable because the set of discontinuity set has measure 1, that is not equal to 0. So this option is not Riemann integrable, right? So this is correct. But the Riemann integrable, this is not true, because if it was Riemann integrable, the measure of the discontinuity set would be 0, but this is not so. So this is false. So here the only correct options are option A and C.